Okay, this class 1 focusing on applications of derivatives. We're mainly looking at solving for maximums and minimums using calculus or otherwise, and then moving on to some Newton's method stuff. We'll also, take a pause and see if the class fills out with anyone doing Unit 1 and 2. If that's not the case, then we can move on to the probability stuff. But, okay, let us continue. So, finding the maximum or minimum of a particular function. So, essentially all we're really doing here in the vast majority of cases is just solving for derivative equals 0. And the reason why is because the maximum or minimum of a function, when it comes to applications, is highly likely to occur at a turning point. And, well, turning points are solved by finding the derivative equal to 0. And so whether you're doing this tech-free or tech-active, you'll find that the procedure is more or less the same thing. There's going to be some beginning of the question where you usually have to figure out what function you even need. Maybe you're creating a volume equation, maybe you're creating an area equation, something to that effect. Or it might just give it to you flat out. Then from there, if you're trying to maximize it, you're often finding the derivative and setting it equal to 0, or if you're in tech active, you might prefer to use your fmin or fmax functions instead. Those are usually going to be a bit more effective because they'll give you always a single solution, and that single solution is the only solution. Whereas when it comes to derivative equals 0, especially when it comes to cubics, you're likely going to get two solutions, and you have to figure out which one of those is the one you're actually looking for. Although, to be perfectly honest, in that case, it's not really all that hard to figure out which one is the right one, because it's often the case that the other turning point will be at the origin, which would be 0, 0, very unlikely to be a maximum. Now, in fact, it will never be a maximum. So all we're going to do to more or less practice this procedure is to just have a look at a few key key examples, of which I have pulled from past exams, so you know this is legit. This is the kinds of questions that you're expected to be able to solve. So let's run through a few. In this case, we are trying to find the value of x, which maximizes the area of the trapezium. Now that's a very specific wording there. Find the value of x which maximizes area. It's not actually asking you to find the maximum area. It's trying to ask you, it's asking you to figure out what value of x would create the largest area for this particular shape. And that's important for formatting your final answer. But okay, as you can see, we've only got a shape. We have no area formula. So if we're trying to maximize area, makes sense to figure out what the area formula would be. This is just trapezium, so feel free to use the trapezium formula. If you don't remember the trapezium formula, you can break this down into triangles and rectangles. It's not particularly challenging there. You would just have to use a bit of trig to get the height of those triangles for your half base times height. You need to do that anyway to get because you need to get the height of the trapezium regardless, so it's not going to really matter one way or the other. In any case, just plugging in all the relevant values, so the a is going to be x, the b is going to be 3x, and to get your h, you either look at the right hand side triangle, or triangle, and the left hand side triangle, doesn't really matter which, and you're just using Pythagoras to figure out the h. A squared plus b squared equals c squared, rearranging for the one that you actually care about. From there, plug that all into your area equation, and you get the area equation purely in terms of a single variable, x. From there, tech active, you're just using fmax to get the x value that would figure out the maximum area. Now, depending on what this function ends up looking like, you might need to put some constraints on x, put a domain on it. The key things to watch out for here are going to be you want to make sure that both x and the area or the volume or whatever it is, both of those quantities are positive, because we're talking about real world quantities here. There's no such thing as negative volume. there is no such thing as negative length. And so since x is a measurement, it is a length, you want to force that to only be positive. Same thing with area. So if it's tech active, or even if it's tech free, depending on how complicated the function is, you might want to give that a sketch and figure out over what domain is this, is both x and my area positive. This function was fairly straightforward though, no need to worry about that. Fmax gives a nice and obvious answer, and you can even double check that by substitution into your function as well. Like if I have x equals 5 root 2, yes, that's a positive number, awesome, but does that also give me a positive area? In this case, it does. The answer that you're supposed to give for this one here is going to be specifically x equals 5 root 2, and it is going to be unitless since none of these have any units on them. Remember, I said find the value of x, not find the maximum area. If it did ask for the maximum area, you would be just substituting that back into your area formula. Tech-free, you can't rely on Fmax, obviously, so you're going to have to rely on your ability to do derivative equals 0. So all I've done here is just start by simplifying what that area formula actually is. We didn't really need to think about it too hard when we were doing the previous one, because we're just going to shove it in Fmax anyway. It's just a copy-paste, but obviously when we're doing it tech-free, simpler is going to be better. From here, we want to find the derivative and set it equal to 0, so we need to be using the appropriate methods to do that. This is going to be a product rule kind of question. Right, you've got 2x multiplied by the square root term in there. Two things multiplying each other, you're now doing product rule. So split it up, u equals 2x, v equals the square root of 100 minus x squared. Find the derivatives of each. Derivative of this one is pretty chill. Derivative of this one, you're going to be using a chain rule. And then from there, yep, just shove it back into the product rule specifically. That'll get you your derivative formula. Nice and nasty. You now have to set that equal to 0 to solve. So what are we going to do here when we have a bit of nastiness? Well, the real nastiness here is the fact that we've got a big fraction involved. And so one of the things you can do here is just multiply both sides by that denominator, thus getting rid of the fraction altogether. Nicely enough, not only does that remove the denominator off of this, but because the denominator was the same thing as this root, anytime you multiply a root by itself, you just get whatever's on the inside left over, which is why this root has now been stripped and you've only got the brackets left over. This is now a quadratic, and a quadratic that is particularly easy solved. Just make sure, again, only x and the area must only ever be positive, so rather than having plus minus root 50, you're just going to drop that plus minus and only use the positive there. Then from there, just simplify the surd all the way down, and that gets you your answer. If you needed to, you would then shove that back into your area formula to get the actual area. But again, as a reminder, we only wanted the x value that maximizes area. Any questions there? Okay, next one up. They typically will like to do this sort of thing here, where what they do is they have a curve and they put a shape inside of that curve. It's a fairly common thing that comes up. You'll see it in the textbook as well. The key thing, again, is going to be to create your area formula, but when it's this kind of question, you'll often find when you try to do that, you're going to have two variables involved. So let's have a look. Part B, well, question B in this case. Find the maximum area of the triangle. This time we are trying to maximize the area itself and give the area as our final answer. So, because it's area we care about, we want an area formula. This is a triangle, so it's going to be half base times height. The base is relatively easy. If we're starting at -1 and ending at positive x, then the distance between those is just going to end up being x plus 1. That's our base. If we then look at our height, just using the terms in the question, the height is going to be y. So if we were trying to do half base times height, we would have half times x plus 1 times y. we have x and y in the equation. We needed some way to remove that y from it. And the way that you'll always do that is by identifying that the same y that exists in the function definition is the same y that exists on this point. And the reason why is because that point is touching the curve. This thing here is a semicircle equation. That's where you're getting this semicircle bit from. The y coordinate here has come from this equation. So if you know that y is the same thing as the square root of 1 minus x squared, we'll just say that. So now when we do our half base times height, everything is now in terms of x. That's the trick you need for these things. So you'll be able to identify these questions pretty quickly. You'll have a curve, you'll have a shape inside of that curve that's touching on some number of points along the curve. You'll get it to a stage where you essentially need to rewrite the function definition inside your area or volume or whatever it ends up being. Everything else here just progresses as normal. So when it came to doing the derivative, for instance, again, this is a product rule. It's something multiplied by something else. So you split those up. I've also expanded it out a little bit and rewrote the root as a with fractional indices, so it's a bit easier to see how that derivative would go. Yeah, diff both, chuck into products rule, and once again, another nastier looking derivative, which we're going to set equal to 0 once more, because we're trying to find the turning point of this function. Again, the nastiness, or at least the main bit of nastiness here, is going to be the fact that there's denominators. Using a very similar tactic from before, choosing the root in particular to multiply both sides by. I guess I could have done the entire denominator. Actually, no, probably. Yeah, no, I could have done the whole denominator. But either way, in this case, I've just elected to only do the root, just to highlight again, when you multiply a root by itself, the root gets stripped off. Then from there, multiply both sides by 2, condense it down to a quadratic, and whatever method you want to do to solve that quadratic is up to you. This one looks like it could be factorized using either the cross product method or the grouping method. But if it's hard to use either of those, feel free to just quadratic formula. You'll get there. Again, this one gave us 2 solutions. Quadratics often do. And so we just want to do a quick sanity check to make sure that, or to figure out which of those x values actually makes sense. This one's ever so slightly different. X, yeah. X is actually allowed to go negative here. And the reason why is because the x is not a measurement, it exists on the actual axes that we're used to, right? The xy axis, the Cartesian plane. And so because x is not directly tied to a length or a measurement, it can actually go negative because x is essentially just wherever you put this b coordinate. Right, so what they've done is they've given a rough idea of what this triangle could look like. If you had your x value here, it would have the height all the way up there. If you put your x value over here, it would be a negative number, and the triangle would be, in this little section over here. And so it's not always the case that x being a negative is bad. It's going to be based off of whether you have it existing on a Cartesian plane or whether the x is literally directly tied to a physical measurement. So we've got 2 solutions. Which of these is going to give the maximum area? One thing you could do is just test, right? Like just plug it in, see what you get. But you could also do a bit of a sanity check and realize that, okay, if x was -1, b would be directly overlapping a, and I'd basically have no triangle. I'd have 0 area. I'd have the minimum, not the maximum. Whereas x being a half, you could imagine if that's -1, that's +1, a half would be roughly there. Seems about right if I were to put a triangle there. Looks like a fairly big area, at least to me. And so yeah, because it didn't ask for the x value, but rather the actual maximum area, we're going to shove that x value back into our area formula to get the area that's involved there. Again, unitless because there were no units. There's no meters, there's no centimeters, there's no nothing in there. Any questions about that one? key thing there is going to be about creating your area formula based off of the function that is bounding the shape. This is just a tech active version. I'm probably just going to use Fmax. Yeah, and because of how this function was created, I did actually end up putting a domain on this one, forcing x to be between -1 and +1. I'm assuming that if I were to not do that, I would have got some other weirder solution. What would have I got? Yeah, not really sure. Either way, bounding it between -1 and 1, reason why I've done that, or at least where those numbers came from, is coming from the fact that this entire shape is forced to be within the semicircle. So if the very end of the semicircle is -1, the other end of it should be +1. And since those are all x values, that's why we have that boundary there. As for the inequalities, whether you use less than or greater or less than or equal to, the general idea that's been, like the general standard for this is that volume equals 0 is considered not valid. And so if you're identifying spots where you do get volume or area quantity equals 0, you consider those non-inclusive. That'll matter for the questions that ask about, like, what's the effective domain of this function? You'll pretty much always put rounded brackets on those because you want area or volume or quantity to be positive, not ever equaling 0. And then here's one final example using a bit more trig this time. Forcing, where is it? Yeah, x is an angle in this case. So how do we handle something like this? Again, it's a trapezium, and we're trying to find the value of x that maximizes the area. So pretty much an identical question to before, but this time the information provided is a bit different. Namely that there's no actual like numerical values here. It's pretty much just p and x. And so we got to figure out how we're going to work it into a specific angle that would maximize area. So again, it's about area, so start with the area formula for the trapezium and set out your appropriate diagram. You want to know what A is, you want to know what B is, you want to know what H is. A is the most obvious by far, it's just going to be equal to P. From there, H would be the next one to try and tackle. So if we hone in on particularly this, we'll notice that we have an angle, we have a hypotenuse, and we have an opposite. Using SOHCAHTOA, or however else you memorize your trig ratio equations, that's going to be the sine equation there. So to get H on its own, you're just going to quickly rearrange from there. Does anyone need a refresher on how like the trig ratio equations work? Let me know, otherwise I'll move on. Okay, so we have A, we have H. Now all we need is B. So how are we going to get that? Very similar way to what we just did for H here. So because B can essentially be distributed into 3 discrete parts, you can now assume that part of B is going to be A, this little bit in the middle, and there's going to be these 2 other sections that belong exclusively to the triangles. So with that in mind, all we now need to do is figure out what that length of the triangle is going to be, label it whatever you like. It's now going to end up being the cos equation that does that. Reason why is because that is now the adjacent, and this is our hypotenuse. You want to get everything in terms of P. That's why we're not like reusing H, for instance. Although I guess technically you could. You probably wouldn't want to though, because now you're adding more trig ratios into the equation than you otherwise would need. It's a lot simpler to use the terms that have less in them. So we have b is going to be a plus 2c. Now that we know what c is, we can just sub that all back in. It comes out to be a relatively nasty thing. Good news is, if we have a look back at the question, multi-choice means it was tech active. It was in the exam too. So we don't really need to do too much effort in the simplification ourselves. We just need it to look as simple as is required for us to make use of it in the CAS. And that's pretty much it. So even if you literally go into your CAS and type in define B as this, define C as this, define A as this, and then just do this in the CAS, it'll simplify that right down for you that way. Then from there, you just Fmax, or you could even do derivative 0 or something to that effect. As for the domain, where that one came from, that one, if you look at how the trapezium is set up, you're basically limited between 0 and 90 degrees. If you had 90 degrees, it would be a rectangle at that point. If you had 0 degrees, you would have a straight line, because there's no angle for it at all. And so anything beyond that just doesn't end up doesn't end up being valid. And so pi on 3 is what we end up with. Maybe another thing you could do would be to, this is like a multi-choice exclusive thing, you could also just look at your spread of answers and then just make that the domain. So whatever the smallest one is and whatever the biggest one is, I think there's pi on 3. Yeah, and whatever the biggest one is, you make that your domain, and then whatever answer gets spat out gets used. Because there's only going to be one valid one for the maximum. Any questions there? Okay. There's a few more examples, I think. So I got one that's on minimizing length. Usually, like a lot of the other questions, are all about maximizing something. This one's about finding the minimum of a thing. There's other equations where the entire thing is fully literal, where they've got exclusively just variables in there. Do we want to keep going through more examples like this, or should we practice some live together? Any preferences? Cool. Alright, I'll just keep going through these then. Okay, so find minimum length between two.
Sorry.
Yeah?
Can you hear me?
Yeah, I can hear you now.
Like live would be better.
Oh, you want to do live? Yeah.
Yeah.
Let's do it. Okay. Let's see. So this is the chapter that's relevant for it. Is there anything super cool in here? There was one that was relatively unique that we haven't really had a look at, which would be something like question 3. Let's give that a go. So it's not as there's no story behind it, there's no area, volume, whatever. It's fairly tame in what it's specifically talking about. However, that doesn't necessarily make it any more easier or difficult as a question. So let's go. Okay, so what's it asking? Given that x plus y is equal to 2, calculate the minimum value of x squared plus y squared. So we have the fact that x plus y is equal to 2. And we want to minimize x squared plus y squared. Feels a bit weird. Usually when we're trying to minimize or maximize something, it's like an area, or a length, or a volume, or a whatever. The fact that it's just 2 terms doesn't really change anything. I could go ahead and define capital A as x squared plus y squared, and suddenly when I say minimize A, it's oh yeah, A could be basically any old area equation. You can think of it however you like. The only difference in this question is that there's no distinct application that you're doing with it. So we still run into the same issue, which is we've got two variables, and when it comes to minimizing or maximizing things, at least tech-free, you're trying to do that by derivative equals 0, and you can't really do the derivative of, well, unless you do spec, you're not going to do the derivative with two variables in there. How might we bring this down to a one variable equation? There's very limited information, so that really constrains our thinking. We know that x plus y is equal to 2, and we want to minimize x squared plus y squared. The problem is that we have two variables that we're trying to minimize. I only want one variable in that expression.
Would that be x squared plus y squared equals 4?
X squared plus y squared equals 4.
2 squared?
As in, like, you're going square, square, square.
Yeah.
If you wanted to do that, you'd have to... Yeah, it doesn't really work that way, because when you square both sides, it's more like that. And then this would expand to x squared, y squared, but also 2xy.
Oh, okay.
But fair enough. I mean, it's nice to see, like, more out of the box thinking for it. The way to go about this one in particular is just to imagine this as like a equals x squared plus y squared, and if I pull up actually one of the previous examples we looked at, where's a good one? Here. It's the exact same strategy that you use for, if we look back at the screen share, this shape enclosed thing, where we had, was like, okay, oh shit, I've got my base in terms of x, but I got my height in terms of y. What did we do there? We did a substitution. So if I know x plus y is equal to 2, I also know that y equals 2 minus x. So rather than have y, I can now just have 2 minus x. So my substitution is now x squared plus y squared, where y is now, oops, almost recursively chucked it back in there. And so we've effectively now removed the y from that equation via our substitution. From here, we'll just expand out. Technically we'll leave it here if we wanted to, but doing the derivative chain rule stuff is kind of, yeah, why bother? Why not just expand it out? 2 squared gets you 4, negative x makes x squared, and that's going to be minus 4x in total. And from there, 2x squared minus 4x plus 4, fully expanded out. We now have our updated formula that we're trying to minimize. So we're trying to minimize this function. How do we minimize a function? Think about what kind of function it is as well. That can help you out with figuring out where the minimum would be. And remember, there's no application here either, so x, y, any of those can be positive or negative. There's no constraints around that. I don't really know where this is going to be on the axes, but I do know it's going to be a parabola, and a positive parabola at that. Doesn't really matter where it goes on the axes. The minimum of this function is always going to be at one specific spot. It's going to be at its turning point. So whether I draw it up here or all the way down here, it really doesn't matter. It's in the same relative spot. It's going to be the turning point of my quadratic. And so from there, derivative equals 0 is going to get our turning point. So we'll get our a dash, that's 4x minus 4, set derivative equal to 0, that's going to get you x equals 1. So in this case, maybe these drawings, either one of these would have been more likely. What's it actually asked? Calculate the minimum value. Okay, cool. So this is not the minimum value, this is just the x value that would give us a minimum value. So remember, we're trying to minimize the equation x squared plus y squared. How are we going to tie this all together? As a reminder, x squared plus y squared is also this. And so if we have, via derivative equals 0, figured out the x value for which there is a minimum, all we're doing from there is plugging that back into our area, or I guess our whatever formula, x squared plus y squared, to get the actual minimum value of that expression. You can do that at this stage, you could do that at this stage, it doesn't really matter. Hell, you could even chuck in the x value into the x squared and chuck the other x in here and then just sum them up later. These are all the exact same equation, just expanded out. So whichever way you want to do is up to you. It was x equals 1. Okay, so it's going to be 2 by 1 squared minus 4 by 1 plus 4. Those are going to cancel and you're left with just a value of 2. That will be the minimum value of x squared plus y squared. It could have just as easily said, hey, area of a shape is x squared plus y squared, minimize it. Any questions there? Alrighty, what's the next one? I guess we'll do something a bit more standard maybe. So this one we see a lot. So question 4, square piece of metal of side length 6 meters, 4 squares are then removed. Keep particular note of the order in which that's mentioned. The square piece of metal was 6 meters and then 4 squares were removed. The metal's then folded to form an open box with height x. So more or less these little cutouts each have dimensions of x by x, and if you fold that up, the height is therefore going to be x. We're trying to show that the volume ends up being this cubic. You'll have the actual picture in front of you. I'm going to obviously draw it. And maybe not label every single side, but just put in the relevant information that each of those squares are x by x. And the important thing to recognize is that it's not this that is 6, it's this that is 6. And that's because of the order in which the information was provided to us. It said the square was initially, well, didn't say the keyword initial, but it said the square is 6 meters of side length, and then 4 squares are now removed. So they're removed after the fact, not before. So if we imagine this all folding up, this 6 is not a length or a width anymore. What we want is this dimension here, which is now going to be what? If 6 is the total thing, you got some x's over here, some x's over here. What's the bit that's left over after cutting out those boxes? Okay, no worries. It's just going to be 6 minus 2x. Right, you started with 6 as your total length, and because these are no longer going to be there because they're folding up into the box, it's 6 minus an x from here, minus an x from here, 6 minus 2x. So, now that it comes to answering the question of proving the volume is a certain cubic, we need to start with the volume of any given cube or a rectangular prism, which is length by width by height. The length and width are going to be identical since it started out as a square. and we're cutting the same amount out of each side, so it's going to remain a square base. And that base is going to be 6 minus 2x. So volume 6 minus 2x all squared, because we have both a length and a width. Right, it's 2 copies of the same dimension. The height is actually just straight up given to you by the question. It literally says height is x, so feel free to go ahead and chuck that directly in there, or again use your diagram and picture it in your head, imagining this box being folded, or this sheet being folded up into a box. The dimensions on this side is going to be the height of your box. What we can see from here is that we're going to get a cubic if we expand that out, so that's good news. And we know we have to expand it out because part A is an expanded cubic. So let's go ahead and do exactly that. Volume is now equal to, so 6 6 is 36, 2 squared is 4, and what's this, 12 minus 12x squared. No, sorry, minus 12x. No, double. So 24. And another x, which we will shove all the way through. 4x cubed minus 24x squared plus 36x. Did I hit it? 4x cubed, 24x squared. Yeah, 36x. Awesome. So yeah, that's pretty much it. And this is following the procedure we more or less outlined, which is start by getting your actual equation. Volume equation is always length by width by height. Just use the right dimensions that were given to you, get it purely in terms of a single variable. The follow-up question on this is going to be something about maximizing or minimizing. Sure enough, if we have a look at it, find the value of x that gives the box its maximum volume, and find the maximum volume. So this is the final sort of variant on this. It's either asking for x, for volume, or both. This is asking for both. It's a cubic. I almost like using this one better because it tells you a bit more information about what the cubic actually looks like. If you're doing this tech-free, when you go ahead and do your derivative equals 0, you're going to get 2 solutions here, and when it's tech-free, you don't really have much to go off of. Maybe we'll get a positive and a negative solution, so perhaps before giving this a sketch, it's a good idea to just do the derivative anyway, and then set it equal to 0 and see. Because if you do get a negative solution, then obviously we're going to go ahead and ignore that potential x value, since this is now talking about volume, and the x is a dimension. So application specific, we're only going to have positives. Anyway, 4 3 is 12, 24, so 48, x and 36, and then setting that equal to 0. 12 is a common factor across the board, so what's that? 4x plus 3, and then, yeah, I mean, basic factorizing is going to be the approach here, -3 and -1. Because -3, -1 multiply out to give 3 and add together to give -4. This one did give us 2 positive solutions, so we can't really just cheat and knock one out. So maybe it's time to sketch. Okay. You could also just plug them back in, but you can see how it's probably not too complicated. Yeah, if you plug it directly in here, it's probably not too bad. There's 2 ways of going about it. If this is a complicated equation, you might not want to sub in, and you might just want to sketch that instead. Alternatively, if it's easier, you can just sub it directly in. Let's maybe even do both. Let's see how we go. So, subbing directly in, so we'd have v of 1 that we're testing. See if that is not how you do a bracket at all. So we're going to have 6 minus 2 all squared times 1. 6 take 2, 4, 4 4s are 16. And then the other option was 3, which is going to be 6 take 2 times 3, so 6. Okay, that's just going straight to 0, so that's easy. Times 3, 0. So, pretty clear. The substitution wasn't too bad. Obviously, don't want to sub that directly into here. You get a very nasty set of equations, or set of things to solve. Better off picking the right, or the path of least resistance there. But okay, so what do we want? We want the maximum. Cool. So we've actually done that job. So I guess that would be the other advantage of subbing in. So long as the algebra isn't particularly challenging, testing both also comes with the advantage of just finding both, right? You have found the x value and you have found the volume that goes along with it. So if the question wanted both to begin with, then that's another more efficient way of going about it rather than sketch. So as far as how you would give your final answer here, you would say x equals 1, v equals 16. Do we have units here? We do this time. Yes. So x is in meters, so all this is now going to be in meters. We have x in meters, we have volume in meters cubed. Bit messy at the end there, but yeah, it's just x is 1 meter, volume is 16 meters cubed. Any questions there? Well, let me know. Otherwise I'll try and spot another one that's interesting. Oh yeah, I guess the other thing would be absolute max and absolute min. So it's mainly in Tech Active that they'll do this, which is, and then in the exam they won't really say absolute, they'll just say max or min, because they're expecting you to have this sort of internalized already, that the maximum or minimum isn't necessarily guaranteed to be a turning point. Like if I tell you to find the maximum of a quadratic that's positive, it doesn't matter whether it's tech-free or not, you know immediately that finding the turning point is probably a bad idea, because a positive quadratic has a minima for its turning point. And so over basically any domain except literally forcing a single point, finding the minimum is going to be a bad idea there. So what you do in these cases where you're trying to find the maximum of something, where you're either quickly identifying that the turning point is not the thing you're looking for, or maybe you're Tech Active and you can just see that the maximum is definitely not at a turning point. This now just becomes a matter of sketch the function, figure out the effective domain, or I guess, sorry, rather sketch the function and then just look. It's very likely to be an endpoint if it's not a turning point. So if you sketch the function, you can see that the biggest spot on that graph occurs at x equals 4. Go ahead and shove x equals 4 back into the quadratic. As for where that came from, that's just a domain, right? Like the question will give you all of this. It'll be up to you to draw that or sketch that on the CAS, and then use your own brain to figure out, okay, that's the highest spot, so I'm going to shove that x value back in. That's what they're meaning by absolute max and min in this question, or I guess in this chapter section. But again, in the actual exam, or the actual SAC, it's unlikely they'll use the keyword absolute in there, and they'll just say find max or find min. And it'll be up to you to make sure you don't accidentally go for a turning point. And again, like tech-free, they don't usually do this to you, unless the function is particularly easy to get an idea of what it looks like. Like this quadratic here would be fairly easy, whereas this cubic would be fairly difficult. So it'd be likely that this would be a tech active one, and this would be a tech free, or could be a tech free one. Okay. Other than that, these are all more or less the same thing. Find the equation, diff equals 0, figure out which one of those is the max or min. There is another topic that I do want to touch on, Newton's method. Do we need to practice any more of these, or are we happy enough to move on? Actually, I think I like Newton's method in the textbook rather than what I've got going on there. So let's go ahead and do that instead. So, Newton's method. What is going on here? This is actually an application of tangent lines, funnily enough. This is exclusively tech active. You will never have to solve a bunch of tangent lines and plug this stuff all in manually. And the reason why becomes fairly obvious when you have a look at what it produces. This is the stuff that you want. It's an iterative thing. You do it over and over again, and you'll see very rapidly you get to these decimals. You get to these like root values that you're approximating. No way in hell you're doing that tech-free. So, what's the whole idea here? There are equations that do not get solved algebraically. The quadratic is not one of them. This has guaranteed solutions. Where you can always find a quadratic solution via the quadratic formula, so long as they exist. But even something as simple as like cubics. Some of those cubics you can't reasonably factorize. You're not going to solve where those x-intercepts are via algebra. So what do? You rely on iterative methods that slowly converge onto an answer, but don't necessarily ever find the exact solution. You only get it to some level of decimal places that you're satisfied with, and you can get it to quite a few decimal places. So, what's the idea? What are we actually iterating on? What we're essentially saying is, if we were to sketch any given graph, you can roughly ballpark where the x-intercepts of that graph are going to be, just by plugging in values and seeing what gets you close to zero, more or less. In the context of actually doing these questions in methods, it will give you a starting point. Like, well, actually, sorry, it depends on the question. So sometimes it'll give you a starting point to start it at. Other times it'll ask you to solve the equation to a number of decimal places. That second question is usually a stupid question, because you don't actually need to use Newton's method to do it. You can just CAS solve and get it exactly. So it's very unlikely you'll get that in the actual SAC or exam. More so, you'll be given a starting point and then have to use Newton's method from there. Anyway, as far as what Newton's method actually is, you take that starting point, and what you're essentially doing is taking a tangent line at that spot. So in this case, the starting point that was given to us is x equals 4. We're saying, okay, my intercept is very likely to be around x equals 4. What you'll notice is, if you take a tangent line at x equals 4 on the curve, so in this case it's the quadratic x squared minus 2, it's the red line here, what you'll notice is that the x-intercept of that tangent line is closer to the red x-intercept than when you started. And so you think, what if I now took this and did a tangent line at that spot instead? Well, then you'll get the yellow line, and you'd realize, oh shit, I got even closer. In fact, I got rapidly closer. If I then took a tangent line here, I'd get even closer. Rinse, repeat over and over again until you basically get infinite decimal places of accuracy. You can see that within 5 iterations, you're already getting to whatever number of decimal places that is, and it's just a bunch of zeros. That's what Newton's method is, fundamentally. The repeated solving of tangent line x-intercepts until you get close enough to your final solution. We don't want to do that though. We want to use a little bit of algebra to help us out, and all we're essentially doing is rearranging, this is the, the gradient point formula, where you got y take y1 equals mx take x1. That's really all that's going on here, and they're essentially just rearranging that into the x-intercept, like the x value itself. And that's where this generic equation comes from for the Newton's method equation. So, now that whole intro is out of the way, how do we actually now use this? How do we do this in methods? The way I've typically suggested that we do this is by defining Newton's method across 3 separate variables in your CAS. The one that you... So, the three things that we need. We need f of x, the function we are trying to find the x-intercept of. we need f dash x, the derivative of that function, and we need something to define the whole Newton's method thing as a whole. So I'm going to just say a of x is f of x. It's the thing that we're starting with. So in this case, or in the example that we had, it was x squared minus 2. So let's just do x squared minus 2. Next up, b of x is going to be my derivative. So derivative of a of x. Specifically do it that way. Don't say derivative of x squared minus 2, say derivative of a of x. The reason why is as soon as you update what a of x actually is for the actual question in the SAC or exam, b of x will therefore update, and so too will c of x, which is the actual Newton's method formula, because everything is written in terms of a of x at the very end. Let me just double check that's right. Yep, x minus f over f dash. F was a, f dash was b, and x is obviously just x. I didn't define it. Nice. Cool, that's better. So how do we now use this? Well, if we take the exact same parameters as per the practice question, it started out at x equals 4. So what we're going to do is shove in x equals 4. What comes out ends up being 9 on 4, or 2.25. If you look back at the screen share, you'll notice that that happens to be the x-intercept of the blue line. Awesome. Where do we go from here? Well, we take that same value, shove it back in. What comes out is the next x-intercept. Rinse, repeat over and over again until you've met whatever parameters the question was asking for. If I start converting these all down to those decimal places, you can even see on the table, the xn table specifically, you'll start to see all those start to match up. And so you're effectively just feeding it back in over and over again until you hit your desired number of decimal places. Any questions about that? Okay, cool. So, the way these questions end up being worded in like an exam scenario or a SAC scenario is going to be one of two things. One is that you're starting with your x value and it says how many iterations did it take to get to a certain number of decimal places. And that's a lot better than just saying what's the value to a number of decimal places, because CAS just tells you that. Right, like if I solve a of x equals 0, all I've got to do is read off how many decimal places. I don't have to do Newton's method in the slightest. And so the way they get around it is they say, hey, how many iterations did it take you to get there for the first time? So for instance, if we use the table of values that was provided to us in the textbook on the screen share, if it said how many iterations did it take to get to 2 decimal places of accuracy, well, first you want to make sure you've got the right number to begin with, and then you just want to look for the first time where those occurred. So in this case, 4.1, 4.2, okay, so the first time that happened was on iteration 4. Just remember that your starting point doesn't count as an iteration, that's iteration 0. And so the answer you would give is 4 iterations to get to 2 decimal places. The other kind of question that I've seen has been more algebraic, where they say, hey, show that this is the Newton's method equation. Don't really put too much thought into like the n's and the n plus 1s here. Those subscripts are there to basically track number of iterations. The algebra does not change in the slightest. In fact, you might have even seen the simplification. If I go back up on the CAS, you know, when I did x minus a over b, it actually condensed that all into the same fraction. That's fundamentally what's happening here. The algebra is not particularly challenging, so I won't cover it too much because there's just one more thing to show, which is the final kind of question, which has nothing to do with calculation in the slightest. It has to do with the limitations of the Newton's method, and why it does not necessarily always provide you a solution. The two ones they want you to understand are the oscillating sequence and the terminating sequence. So first up, oscillating sequence. What does that mean? It means your Newton's method gets stuck in a loop, and it keeps repeating over and over again, hitting the exact same x-intercepts, never actually converging onto a single solution. A classic example of this would be something to the effect of the cubic here. A circular function could also do it. The key thing... What's the key thing here? It's got something to do with the odd property of it, and by odd I literally mean like an odd function, how it's got this sort of diagonal-ish symmetry to it. What's going on here is there's actually a line there, by the way. I don't know why my textbook didn't print it out properly. There's supposed to be another coloured line. But anyway, let's say I take my tangent line at this spot, I get the hidden white line, and it cuts here. It's like, okay, cool. Then I take my tangent line up here, it cuts here. But that spot happens to be the same as where I just started. It oscillates over and over again. It never actually reaches the x-intercept. That's oscillating. Terminating sequence means there is no additional x-intercept. And the only way that can happen is if you take your tangent line at a stationary point. What's so bad about that? Stationary points are flat. So if I take my tangent line at the turning point, it will be 100% horizontal. It will not touch the x-axis anymore, and therefore you will not have another x-intercept to work with. That is the terminating sequence. The question that you get in the SAC or the exam won't necessarily be like, hey, why doesn't Newton's method work? The one that I remember from an exam was something to the effect of, why would it be a bad idea to choose this starting point for Newton's method? And you have to then go into your head and be like, okay, well there's some things that force it not to work. It'll either oscillate over and over again, or it'll terminate. Terminating is all about the stationary points, and oscillating, that's a fair bit harder to prove, but the way to go about it will probably be to say, well, if it's not terminating, it's got to be oscillating. So if I don't have a stationary point as the issue, then it's got to be this issue, and you can test that out, see if it ends up oscillating. And that's Newton's method. They also chuck in a bit of pseudocode for this sort of stuff as well, that we have actually already covered in our curriculum. So if anyone still needs to cover that for the first time or revise that, we can definitely do so. But for now, with 2 minutes to spare, we're not going to get nearly there. Yeah, that's pretty much it. Is there any question that we could reasonably do at this stage? Maybe we can show this a little bit. So, how do we get to that? How does Newton's method give us that equation? Well, if we recall what Newton's method is all about, it is the equation xn plus 1 is equal to xn minus f of xn over f dash of xn. Again, the n's, the n plus 1s, aren't particularly relevant. Oh no, everyone's gone. It's fine. Oh well, at least the recording will have it. So, what are we doing from there? Well, f of xn is therefore just x cubed minus 3. And f dash of xn is now 3x squared, xn squared. From there, you have xn minus, no, I didn't put it in there either, xn cubed minus 3 over 3xn squared, and then all you're doing is bringing that into the same denominator, so multiplying it by 3xn squared, making this 3xn cubed. 3xn cubed minus xn cubed is now 2xn cubed. minus 3 over 3xn squared, which I bloody well hope I got right, which I did. Awesome. Never mind, there's a plus. What do you mean there's a plus? What? Did I get the function wrong? Yeah, that doesn't seem... Oh, it's the minus. Yeah. It's minusing the full thing, so that's now going to become a plus. Cool. Enjoy, whoever's watching the recording.